Today is lecture 31. We've got lecture 31 today, 32 Wednesday, 33 Friday, 34 next Monday. Our exam next Wednesday, exam 3. Then Friday of next week is the review for the final exam. And then we have the final exam the week after that. And as we go through new content, I am still going to be reviewing old content. So for example, to start lecture 31 off, I'm going to talk about the mean value theorem again and show you some really important examples to understand the details of how theorems work, so to speak. So that'll be really important. The Squeeze Theorem is something a little extra that I want to briefly talk about. More importantly, I want to introduce L'Hopital's rule. And then that'll probably go over into lecture B, where we'll also look at one-dimensional motion, definite integrals, and the fundamental theorem of calculus. Let's start by writing the mean value theorem up on the board. MVT for short. It's a theorem about functions that are nice. They are continuous on a closed interval and differentiable on the open interval. Suppose f is continuous on a certain closed interval from a to b. So a and b are numbers. A is less than b, that's assumed in this notation. If you imagine them on a number line, a right here and b right here, this is all the numbers between a and b, including the endpoints. The square brackets means include the endpoints. And differentiable has a derivative on the open interval from a to b. Why is that one closed and this one open? I'll show you today. There's an example that will illustrate that this is good enough. We could assume it's differentiable in the closed interval as well, but it's good enough to just assume the open interval. Then there is a number C that's an element of the open interval from a to b. Again, this symbol here means is an element of or is in this set. Such that, how do I remember this? I've said it already. The slope of the tangent line at C equals the slope of the secant line between these 2 points here, A, comma, f of A, and B, comma, f of B. The secant line connects those. There's at least one number C, perhaps right about here, where the slope of the tangent is the same as the slope of the secant. Those 2 lines are parallel. F prime of C equals f of B minus f of A, all divided by B minus A. That's the slope of a tangent line, this is the slope of that secant line. These examples that I want to talk about pretty quickly can also be found in my blog. There's a link to a blog post I made back in January of 2019, infinityisreallybig.com. It's called Deconstructing the Mean Value Theorem Part 1. It's got a lot of extra theoretical stuff in it as well, but these examples are there, and it's the examples we want to focus on. Example 1. A discontinuous function that fails the conclusion of the mean value theorem. What does this mean? Well, first of all, it's a function that's not continuous. I made just one point of discontinuity. It's continuous everywhere else. So it does fail the hypotheses. It's not continuous. Come back over here to see where I'm pointing here. It's not continuous on this interval. So you should not expect it to necessarily satisfy the conclusion. There won't necessarily be a C where the slope of the tangent is the slope of the secant. And that is the case here. It will fail. And here's the example. It's piecewise. It's equal to 2x if x is between 0 and 1/2, and 2x minus 1 if x is between 1/2 and 1. And here's its graph. You can see it's a piecewise function. 2 straight lines that are disconnected. This is not a continuous function. Guess I can't quite draw it on the wall here, but the secant line between a comma f of a and b comma f of b would be a line like this that I won't actually draw on the wall, did touch the wall. There's your secant line. It's got a slope of 1. And there's no point between the 0 and 1 where the slope of the tangent is equal to 1 because these two lines have a slope of 2. And they are both the tangent lines for their respective points because they're straight. So just failing to be continuous at one point can make the conclusion not work. There is no number c so that f prime of c equals 1. The slope of the tangent is the slope of the secant. Okay? So that's an important kind of example to keep in your mind. Certainly if the function is discontinuous, the conclusion of the mean value theorem may not hold because the function doesn't satisfy the hypothesis, so you shouldn't expect the conclusion to hold. Second example. Here's a discontinuous function that actually does satisfy the conclusion of the mean value theorem. So come back over here. It will be discontinuous. It will not satisfy this. So while there's no guarantee from the theorem that it's going to satisfy the conclusion, this function does happen to satisfy the conclusion. That can happen too. That's something else I want you to realize. This one's also piecewise. It looks like this. It's x when x is between 0 and 1/2, and x squared if x is between 1/2 and 1. And the secant line between f of 0, 0 comma f of 0 and 1 comma f of 1 has a slope of 1. And every point along here has a tangent line that also has a slope of 1, because that's a straight line with a slope of 1. For every number c between 0 and 1/2, the conclusion of the mean value theorem holds. That's kind of amazing. Even though this function is not continuous. So what I'm trying to get into your mind is just a realization that sometimes if the hypotheses do not hold, the conclusion will not hold. But sometimes, even if the hypotheses do not hold, the conclusion will hold. Why did it just happen to be the case for that example? The theorem really has nothing to say about these examples. The theorem only applies to functions where the hypotheses are true, are satisfied, and neither of these first two examples are the hypotheses satisfied. The second one isn't satisfied either. Remember, if the function is differentiable, it's also continuous. This is part of our overall broad review. I'm going to be weaving in review for the whole course as we go here. If the function is differentiable, it's also continuous. So if it's not continuous, it's not differentiable. That function is not continuous, it's also not differentiable. Yet it still satisfies the conclusion, in fact, for infinite many c's. Here's the third example. Here's a continuous function that's not differentiable. And it fails the conclusion of the mean value theorem. So it partially, come back over here again, partially satisfies the hypotheses. It is continuous on the closed interval, but it's not differentiable there. It's your old friend, the absolute value function. Its graph has a corner in it. F of x is the absolute value of x. Its graph looks like a V. It is continuous everywhere. You can draw it without picking up your writing utensil. But it does fail to be differentiable at the origin. This V shape, that corner there, does not smooth out as you zoom in. It always looks like a V. There is no tangent line at this point. And in fact, the conclusion of the mean value theorem fails. There is no number c between -1 and 1, where the slope of the tangent is the slope of the secant. The secant here is just a horizontal line, slope of 0. But there's no point where the tangent line has a slope of 0, including at 0. There is no tangent line there, because the graph has a corner. It's not smooth. So we failed the hypotheses at just one point. And in this example, the conclusion was not satisfied. However, just like with the continuity, you might still fail these hypotheses, but the conclusion still could be true. And that's what's going to happen in the next example, I believe. Well, actually, that's going to be our fifth example. Here's a function I'm going to show you that's continuous on the closed interval and differentiable in the open interval. In other words, it does satisfy the hypotheses of the mean value theorem, and therefore the conclusion must hold. There must be a c. I did make this one a little funny in the sense that I made it fail to be differentiable at the endpoints. How can you come up with such a function? The inverse sine function is such a function, actually. Its graph looks like this, and it actually does fail to be differentiable at the extremes of the graph, down here and up here, because the slope approaches infinity. The slope is undefined at those points. But it does satisfy the hypotheses of the mean value theorem. It is continuous on the closed interval from -1 to 1. It is also differentiable on the open interval from -1 to 1, not differentiable at the endpoints. So it does satisfy the hypotheses, just barely, you might say. So there must be at least one c where the slope of the tangent equals the slope of the secant. In fact, there are two such c's. You can even solve for them. The slope of the secant line turns out to be pi over 2. The rise is pi over 2 minus negative pi over 2. Second coordinate of that point minus the second coordinate of this point, which is pi. The distance vertically here between those points is pi. And the run is 2, from -1 to 1. The slope of that secant line is pi over 2. Remember, here's review, the derivative of the inverse sine function is that. Do you remember that? That did show up on one gateway version. When x is strictly between -1 and 1. This is undefined when x is plus or minus 1. That's one hint that perhaps this function is not differentiable at the endpoints, though it's not really a proof of that. We would be dividing by 0 if we tried to plug in plus or minus 1 for x. But there is at least one c, in fact, two c's. If you set the derivative equal to pi over 2, I should put the word set here, but I forgot to. You will find that c is approximately that. Well, it's exactly these two possibilities, which are approximately these two numbers. And you should, on the third exam, for example, be able to solve for that c if I asked you to. Solve that equation for x. You could call it c right from the start if you want. How do you solve this? Well, it'd be good to get rid of the square root. You can square both sides. Then you could cross multiply or effectively just flip the fractions. Solve for x. What did I do there? I did a couple steps at once. I added x squared to both sides. I subtracted 4 over pi squared from both sides, and I also switched around the direction. I guess that was 3 steps. Get a common denominator here of pi squared. This is the same as pi squared minus 4 over pi squared. And your denominator is pi squared. Now take the plus or minus square root. X, or c, is the plus or minus square root of the top divided by the square root of the bottom, and the square root of the bottom is just pi. So you should be able to do that kind of algebra if I asked you to in, say, the third exam to verify this. Fifth example is an example, maybe you should have switched around examples 4 and 5. This is an example of a non-differentiable function that still satisfies the conclusion of mean value. It's going to be continuous on the closed interval. It will fail to be differentiable at one point, so it will not satisfy the hypotheses, but it will turn out it just happens to satisfy the conclusion. But there's no guarantee of that unless you actually check it. The example is the cube root function, and the interval is from -1 to 1. Here's the graph. It's a smooth graph, you might say. There's no corners in it, but there's a problem right there. What's the problem? This is review of chapter 2. What's the problem with the differentiability at that point? The derivative doesn't exist because the tangent line is vertical. There is a tangent line, you might say. It's just a vertical line. Slope is undefined. So we would still say the function is not differentiable at 0. It does not satisfy the hypotheses of the mean value theorem. But it does happen to satisfy the conclusion, which C is plus or minus 1 over 3 root 3. Set the derivative equal to 1, solve for C. And I forgot my word set. These are problems where I'm setting these derivatives equal to constants that are not 0, so that I can solve for the C from the mean value theorem. This doesn't prove the mean value theorem, and in fact, the mean value theorem again doesn't apply to this example. But it's obviously related to the mean value theorem, the way it's structured, and what the conclusion happens. Theorems are guarantees that something will be true, a conclusion will be true, down here, if you know the hypotheses are true. So if you know you have a function that satisfies both of these conditions, it will be guaranteed to satisfy this condition. But if it does not satisfy these, it may or may not satisfy the conclusion. There's just no guarantee from the theorem. The theorem does not apply to that situation. Here's something else that I'm going to use as a review. Going back to our wild example from lecture 30 last Monday. It's going to be an application of something called the Squeeze Theorem. Do you remember our wild example? This one here? That's the one whose graph oscillates infinitely often on any little open interval around 0, though because of the x squared in front of the sine of 1 over x, the oscillations get smaller and smaller. Because as x goes to 0, x squared goes to 0 really fast, actually. And the 1/2 x in front of it makes the tangent line at 0 have a slope that's positive. This is the graph that looks about like this. And it oscillates infinitely often, which I obviously cannot draw. Near 0. I'm not drawing it very well, okay, right? I'm not being very careful, other than to just hint that it's oscillating infinitely often. And we saw last Monday, as you zoom in closer and closer to the origin, it does look more and more like a straight line with the slope of 1/2. The derivative, in fact, at 0 is 1/2. But I said it was not increasing on any little interval around 0 because it turns out the oscillations are still there, though you just can't see them. It's so small. But how do you confirm f prime of 0 is 1/2? Last Monday we did confirm that f prime of x, when x is not 0, equals this. You should be able to check that. Derivative of 1/2 x is just 1/2. The derivative of this can be found with the product rule and the chain rule as well. And it simplifies to the top there. But why do we know when x is 0 that f prime of 0 is 1/2? You have to go back to the limit definition of the derivative. So this is review as well. Remember, f prime of 0 in this case is the limit as h goes to 0. Of f of 0 plus h minus f of 0 divided by h. The a here is 0. In general, you're going to have an a there and there. But 0 plus h is just h. That's why you see an f of h here. When you take this limit, remember with limits, it's irrelevant what happens when h equals 0. We're just letting h approach 0 without actually equaling it. So what that means is I can use this formula on the top there when h is non-zero. When h is 0, like you see right here, when I want to evaluate f of 0, I do need, I guess I should have been pointing here. I do need that fact that this function is defined to be 0 when x is 0. Really, there's a minus 0 here as well. I just didn't put it. I brought the division by h out in front as a multiplication by 1 over h. F of h is this. I just want to find this limit now. You can multiply the 1 over h through the parentheses. 1 over h times 1/2 h is just 1/2. The h's cancel. 1 over h times this, the h's cancel as well, giving me this. And I claim the limit of that is 0. So the final answer is 1/2. How would you prove that this limit is 0? You need a theorem. It's called the Squeeze Theorem. I'm not going to state the theorem, but I'll give you the basic idea of it. This last line is true. This limit equals 0. Why? Because this function here, h sine of 1 over h, is always between these two functions, the negative of the absolute value of h and the positive of the absolute value of h when h is non-zero. And both of those functions do go to 0 as h goes to 0. So this graph, this function is squeezed between these two functions. It must also go to 0. Here's a picture showing you how. So the red graph is h sine of 1 over h. Think of the horizontal axis here as being an h-axis. And this V shape like that, that's the absolute value of h. This V shape like this is the negative of the absolute value of h. The red graph has to get squeezed between those two graphs. Because sine is always between -1 and 1. That's the reason. Sine of any input, any real number input, is always between -1 and 1. So the product here must always be between -1 times the absolute value of h and +1 times the absolute value of h. You can see in the picture. So sometimes when you calculate limits, theorems must be used. I'm, again, not stating this Squeeze theorem, but I'm just trying to give you the basic idea. And if I drew something like this on exam 3, just from this picture, you should be able to say the red graph goes to 0. I'm not going to actually have you prove anything with the Squeeze theorem, because I don't want to really emphasize it a whole lot here. But just make you aware of it. Sometimes limits have to be evaluated with theorems. In this case, the fact that this is true and this is true is enough to guarantee that this must be squeezed towards 0. Its limit is 0, just like I have up here. These are all subtle points, but they're worth talking about to help you understand some details better. If you're going to fully understand calculus, you do need to understand details better. More discussion of limits is something called L'Hopital's rule. L'Hopital was actually not a mathematician. He was a French aristocrat back in the 1700s, rich person. And he got one of the Bernoulli brothers, I believe, to write a book for him, but his name went on the book, not Bernoulli, even though Bernoulli wrote it. L'Hopital did like math, he just wasn't a mathematician. So he hired Bernoulli to write a book, and then he put his own name on it. And one of the rules in that book was this thing that we now call L'Hopital's rule. And in the simplest case, what does it do? It helps us evaluate certain limits, certain special limits. We're going to see applications of L'Hopital's rule later this week when we do the data modeling. On Wednesday and Friday, we're going to get real in-depth into our new applications, data modeling and fluid flow. Simplest kind of fluid flow. Just overall talking about how flow rates can change. We're not going to get into details like how does water flow through pipes. That's going to be beyond what we do. So we're going to apply it to data models called density functions. It applies to so-called indeterminate forms. Here's an example. Suppose you'd like to calculate the limit as x goes to 0 of sine of x over x. I'm writing this first because there's your general form of the problem. The general form of the problem, where you use L'Hopital's rule in the most basic situation, is taking a limit of the ratio of two functions. However, this is really important, both of those functions have to go to 0 as x approaches a. A is 0 in this case. Sine of x and x, those two separate functions that I'm putting in a fraction, do indeed both go to 0 as x goes to 0. their graphs. Like this, here's your graph of your the sine function. And the graph of the function y equals x. I'll just label it x. Now, put y's in there. Two functions that both go to 0 as x goes to 0. And in fact, they're very close together as x goes to 0. In fact, y equals x is the tangent line to sine of x at x equals 0. They're so close together, in fact, that when you take their ratio, it's got to be close to 1 when x is close to 0. And in fact, that is true, and this limit does end up equaling 1. But to verify with this L'Hopital's rule, again, first you need to make sure that both the top and the bottom are going to 0. It's called a 0 over 0 indeterminate form. And we actually can go ahead and write 0 over 0, even though that's undefined, but then label it indeterminate form. And what L'Hopital's rule says to do in this simple situation is to take the derivative of the top divided by the derivative of the bottom when you plug in x equals a, which is 0 in this case. Here's what I mean. In this case, it's f prime of 0 divided by g prime of 0. The top function, sine of x, has a derivative equal to cosine of x, so I plug in 0 into cosine. The bottom function, x, has a derivative equal to 1, so I put a 1 there. Cosine of 0 is 1. 1 over 1 is 1. There's a basic application of L'Hopital's. Let me verbally say what I just have been saying these last couple of minutes. It's a special trick, you might say, that allows you to evaluate certain special limits. This is one of the most basic examples. A limit of a ratio in this case, as x approaches some number a, which is 0 in this case, where the top function, f of x, happens to be sine of x in this case, and the bottom function, g of x, happens to be x. In that situation, as long as we're not dividing by 0 here, I should have added, as long as g prime of 0 is non-zero, this ratio will be the answer. Take the derivative of the top, plug in 0. Take the derivative of the bottom, plug in 0, and form that ratio. This only works, though, in these special kind of situations. The 0 over 0 indeterminate form in this case. Both of these functions, the top and the bottom, go to 0 as x goes to 0. Why does it work? That's basically an application of local linearity. Here's an approximate equation you should know for, especially the final exam. You've used it on exam 2. Right, there's your linear approximation. It's essentially the equation of the tangent line here. You've seen this before. If f of a happens to be 0, which it is here, sine of 0 is 0, that term goes away. It becomes 0. You can say the same kind of thing about the g function. If g of a is 0, this term goes away, and it simplifies to this. And therefore, the ratio f of x divided by g of x is approximately the ratio of these two things. That divided by that. And the x minus a's cancel, leaving me with f prime of a divided by g prime of a. Again, as long as we're not dividing by 0. That's not a proof, but it's the intuitive reason why L'Hopital's really works. That's why I'm showing it. You can think about it graphically as well. We will probably do that more on Wednesday. In section, I believe it's 4.7 of the book, you should also read that carefully and see how the book thinks about it graphically. We'll do a couple more examples, then we'll take our break. A couple more L'Hopital rule examples. I modified the previous example a little bit. But it still is a situation where L'Hopital's rule applies. And by the way, if you ever try using L'Hopital's rule when it does not apply, when you should not use it, you'll probably get the wrong answer. So you've got to make sure that it's a situation where it applies. and this is 1, both the top and the bottom, sine of 2x and 3x, go to 0 as x goes to 0. This is a 0 over 0 indeterminate form like I wrote over here. Therefore, you can use L'Hopital's rule. And what it says to do in this simplest of situations, there are more complicated situations where this doesn't quite work, is take the derivative of the top and the derivative of the bottom, plug in 0, and form a new fraction, like this. The derivative of sine of 2x is 2 cos 2x. The derivative of 3x is 3. Plug 0 into both of those functions. Once again, cosine of 0 is 1. So the final answer here is 2/3. And you can check this graphically, and I encourage you to do that after class. Graph this function sine of 2x over 3x, and you'll see in your calculator that it does seem to approach 2/3 as x goes to 0. By the way, it is undefined at 0, right? You can't plug in 0 into that. It's undefined. But it does not have a vertical asymptote, it's got a hole in the graph. And this calculation helps you figure out the second coordinate of that hole. One more example. Now f of x is e to the 5x minus 1, and g of x is 4x. By the way, one other word of warning here. This is not using the quotient rule. I hope that's pretty obvious. I'm not taking the derivative of this ratio. I'm not using the quotient rule. I'm taking the derivative of the bottom and top individually and forming a new fraction where I plug in 0 as long as I don't divide by 0. And here's what it turns out to be. The derivative of e to the 5x minus 1 is 5e to the 5x minus 0. I'm going to plug in 0 into 5e to the 5x, like this. E to the 0 is 1, 5 times 1 is 5. G of x is 4x, g prime of x would be the constant 4. If I plug in 0 into that constant, I get 4. This limit is 5/4. Okay, so these are, again, some basic applications of L'Hopital's. Let's take our break right now.